when it's a box beam, it shares the Q. So one Q go to the left, one Q go to the right. You have to divide by 2. Over here, you don't need to divide by 2. Does that make sense? Right?
Yes.
Yeah. So that's the only thing. Okay. Again, this is one of the most confusing topic around. Okay. I believe you guys have taken 2P. You have not seen a topic that is so much I won't call it a lot of math, but a lot of rules. Yes or no? It's one of those that it's not just one formula. Keep on beating the formula down. You don't need to analyze your fight. No, you have to analyze. Okay, so that's where this topic is so-called slightly more difficult, but it's not really that difficult, right?
Eugene, one more question.
Yes.
Will we always be given points to analyze, like A, B, and C, or where will there be times where we have to pick, like, oh, is the shear stress like maximum at like point of our choosing?
Yeah. So usually I can do either way. Okay, I can ask you to like calculate specific point, or I give you a specific point like this. You determine where the maximum shearing stress is. Okay.
Okay.
Okay. Right. So this is the end. I hope this is clearer now to all of you. Okay, compared to what I've done last week. Right. I hope this is clearer now. That's why I decided to go through it again. So the next thing now that we're going to do. Okay, now I can give you any cross section. I can give you the whole textbook. You apply what I teach you, you'll be good to go. Okay, that's the level of confidence I want you to have. Right, the next one is a different topic already. Okay, so we're going to look at this beam now. Right. So now I'm going to teach a asymmetry. Okay, asymmetry. Loading of a thin wall member. Now this is only true if you have thin wall member only. Thick wall, it will not happen at all. Okay, so thick wall, this set of rules will not work. Okay, and I'll explain to you why later on. So on your textbook, it's on 6.9. So if we have a channel now, okay, we have channel. You can see a channel now, right? Then this structure we are loaded this way is under the condition of symmetrical loading. So if I were to have drop transformation, so if this is my y, this is my x, and over here, this is my z, right? So for this case, when the structure is deformed, so it's a built-in structure, cantilever beam. At one end is built-in, at the other end is P. Okay, so what you see down here is the structure will deflect or will bend. Okay, the structure will bend in the y-x plane only, right? It will bend what xy plane. So if I have to draw the deformation, okay, so the deformation will look like this. Okay, so xy plane only. Okay. So xy plane only. Okay, so I'm going to shade the plane that is going to, so it's bending on this plane only. So the deformation of the structure, so for this case, right, if we look at the cross-section view over here, so we'll look at the cross-section view. This is your Y, this is your Z, there's your rotation about X, right? So what we see, the deformation of the structure is only by bending and the deflection will occur on the XY plane only. Okay. So most of the structure we analyze up to now, right, will deflect on one single plane only. So from here, you can apply two sets of formula where you have shear in the x direction, or the normal stress in the x direction is equal to minus mz over izz multiplied by y. Don't forget all this, okay? And then the shear xy is equal to vy over izz qz multiplied by thickness. Okay, so this is what we call symmetry loading. So the next one, we're going to look at condition of unsymmetrical loading. So now this is different now. Okay, so what is the difference? So I'm going to capture the other images. Right. So the problem now is this. Okay. Now your structure is applied differently, right? Your structure is applied. So if you look at the one on the top, is under symmetrical load, and the one on the bottom, we classify it to be unsymmetrical load. So can anyone tell me what you see different now between the two? Can anyone tell me? If I'm going to, can anyone tell me what you see different now? So the top one is symmetry. The bottom one is unsymmetry, right? And if you look at the cross section, right, the cross section, you can see that the structure is loaded. I mean, the vectors are still the same, but there's something with the cross-sectional view of the structure. Can anyone tell me what is it, please? Thank you. So I'll give you guys a hint, which is stiffer. The one, so if we look at the cross-section over here, which is a stiffer section from the centroid, the left-hand side or the right-hand side relative from the centroid axis? Anyone?
Left-hand side?
Yeah. So if you look at this structure over here, where I'm shading now, this side has a higher what? Stiffness. Hey, higher. Right. Where else? The right hand side. Okay, so this region over here, right? because of the thickness or there's a gap. Okay, you see there's a gap. So this side relative to the centroid. Okay, so this is our centroid. All right, over this side it has lower what? Stiffness. So when that's the case, okay, when that's the case, right? So the structure. So if I were to draw our transformation again, so this is your y, x, and z. Okay, the structure will bend still in the what? Still in the xy plane, but and not but, sorry, there's nothing bad about it, and a twist about the x-axis. So is this twist that is going to cause us the problem? Okay, is this twist that's going to cause us a problem? Okay, so this formula over here, so I will call this equation 1 and equation 2. So equation 1 and 2, especially equation number 2, okay, equation number 2 is only valid when there is no twisting, right? Twisting is a shear. Why twisting is a shear? Because if you were when do you see twisting as a topic, where you have the shear stress is equal to TR over what? J. And then this is also due to what? This twisting is due to a what? Torsion. Okay, so this formula is the shear is due to what? Due to torsion. And the deformation is by twisting. Now the question is, how can we apply equation 2 to this structure over here? Okay, how can we apply equation 2? So in order to apply equation 2, right, there's no twisting. You have to get rid of the what?
Twisting.
Yeah. So how do we do that, right? Yes. Anyone?
Can you just subtract it from the TXY? Like minus the torque.
You are partly right over here. Okay, so we have to compensate. When you say minus, means we have to what? We have to compensate, right? We somehow have to compensate. So the only way to compensate, right? The only way to compensate is to do this. So I'm going to copy the third image. So the only way to do this okay. So the only way to eliminate the twisting is to offset the shear force P for this case. It can be also be V by distance of E. Okay, right? So this distance of